Okay, so let's get started. So this class, we're going to start a new chapter about the aerosol chemical analysis. Okay. So before we do that, let's first talk about the course project. So as you can see from the syllabus, so this class, since it's a graduate level class, there's a course project that will take a significant fraction of the grade, right? So in terms of the course project, so I want you to use what you have learned from this class. Okay, so both on the, let's say, the physical characterization or the chemical characterization, and then to identify a problem and then propose a method to solve that problem. Okay, so it can be both. It can be, let's say, you identify a problem that, or let's say, an atmospheric constituent or property that is still impossible or difficult to measure, and propose an approach for its measurement and the associated benefits and the reasons for doing so, or to identify a weakness in the current particle measurement techniques. For example, you can talk about, let's say, the particle sensors are not able to provide the aerosol or accurate aerosol size distribution, right? So, or you can create additional aerosol measurement to fill in this gap, okay? Or basically to propose an approach to address it and point out the associated benefits. Okay, so because of that, this project will require some creativity as well as understanding of the course material. Okay, so in terms of, let's say, preparing for the course project and also submitting the course project, so we can take a look at the remaining time or the class schedule, let's say in the later of this semester. Okay, so right now we're in the week of October, right? And then basically there's going to be an abstract for your course project that's due on November 7th. Okay, so this is basically 2 weeks from now. So in the abstract, you can talk about the project that you would like to work on, and also to propose, and I mean, just a general description of what new methods you are going to propose. I think many of you actually work on the aerosol projects and you're trying to find out new methods to solve certain problems, right? So that's your uniqueness. And you can just mention those projects and use that as a part of your course project. Okay, so that's the abstract, and then you will have the, let's say, more than close to 1 month of project, 1 month of time to work on this project. And then there's going to be a report due, and then you will make the presentations during our class time. Okay, so in terms of the project presentation, it will be similar to the journal review sessions, that you will have 12-minute long presentations followed by a 3-minute question and answer. And then the presentations will be scored by me and others in the teams, right, or other members in our class. And then in terms of the report, so it is due before the presentation on November 30th. So basically that's the first class or the first batch of the presentations. So for the written report, it should contain the following sections, including the background, which type of atmospheric constituent that you are trying to measure, and also to point out the current limitations in aerosol instruments, and mention your proposed methods, and discuss your method, and also mention the associated benefits and the conclusion. So in terms of the project length or the report length, you will use 12 point font size times New Roman font, single line spacing, and then 1-inch margin, and it should be 3 pages, excluding the references. Okay, 3 pages, I think it's okay. And then try to include more than 2 to 3 figures about the instrumentation or your proposed data analysis methods. So for the scoring of the reports, it will be done by me. Okay, so overall, this is the general idea about the course project. Okay, so now let's get started onto the aerosol chemical analysis. So if you recall, we're now more than halfway through this semester, and we have been focusing on a lot of our efforts onto the aerosol physical analysis. So basically, they include the number concentration. We said that we could use electrometers or condensation particle counters to monitor the number of these aerosols. We also talked about the mass concentration measurement. We could use the impactor, use the filters, and so on to monitor the mass. And then we combine these thoughts and then mention how we can measure the size distribution. And as you recall, the differential mobility analyzer or the scanning mobility particle sizer, the SMPS, actually is a quite important concept in our class, right? So those are focusing on the aerosol physical analysis. So what about the chemical analysis? We haven't talked about chemical analysis yet, or maybe a little bit when we talk about the mass concentration analysis, right? So this class will introduce a few chemical analysis method, and then we will probably use most of the time talking about the mass spectrometers. But before the mass spectrometers, we'll just talk about some offline measurement methods, right? So one of them is called the particle into liquid sampler, or the PILS. So the PILS is currently commercialized by the Brettel, a company called Brettel, which also manufactures other types of aerosol instruments. It was first invented by Rodney Weber at the Georgia Tech. Okay, so if you think about the measurement or the methods for the PILS, basically it's a liquid, let's say, sample extractor that converts the aerosols into liquid samples. Because we know that there are many advanced instruments in the, let's say, the water treatment or wastewater treatment field that they could use their established mass spectrometers or the liquid, let's say, chromatography to monitor the composition of these liquids. So why can't we just convert all of these aerosols into the liquid? We could do that, right? So, I mean, the mechanism is quite similar to the CPC, except that here we're using high temperature vapor. It's like close to 100 degrees Celsius vapor into this tube here. And also the flow rate is relatively high. So you're creating this turbulent mixing or turbulent flow inside the tube. And then in this way, you can capture the particles better. So the aerosols will be introduced into the tube here. And then basically inside this tube, the temperature gradually decrease, and then the water vapor is going to condense onto these aerosols, and then they grow into supermicron droplets, and further they can get collected onto this impactor here, which converts into a liquid stream, right? So further, you can introduce the flow here to wash this liquid out, and then you can basically get the liquid samples. And with the liquid samples, you can do different types of chemical analysis. For example, you can use the ion chromatography to look at ionic composition of these of aerosols in these solutions, right? So basically, in the IC here, what it does is that the different chemical compositions will have different speed or migration speed when they're running through the column here. Some of the species can run faster, some of the species will run slower, right? So for different species, based on their basically elution time or this retention time here, you're going to get chemical compositions with different, or the liquid with different compositions reaching finally to the exit, right? And there can also be calibration processes which try to relate this elution time to the chemical composition. So basically by using these IC technique, we can get a general understanding of which group of chemicals are there in this liquid here. So basically we can tell what's the fraction of the sulfate, nitrate, ammonia, or organics in this liquid here. And it can also give you the composition of several metal ions that are existing in this liquid. Okay, so this is the PILS method. So actually for the PILS, one feature is that it can basically, if it measures the organics composition, it can only measure the water soluble organics, right? If they're not soluble in the water, then they will just get, for example, when they're being, let's say, when they're growing in this tube, they don't grow as much compared to the water soluble organic carbon, right? And then also when they're being analyzed, even if they get into this solution here, there is going to be a separation of different phase here, right? Different composition here. So you won't be able to get a homogeneous characterization, homogeneous solution that contains these water insoluble organic carbon, right? So basically, people use this Pugh's method to analyze what's the water-soluble organic carbon that's existing in the aerosols. So this is the OCEC analyzer, organic carbon, elemental carbon analyzer, right? So we mentioned about this when we talk about the mass measurement techniques, right? So the OCEC analyzer basically uses the oxidation chamber, right? And then it has a sensor that measures the carbon dioxide concentration, NDIR sensor, to characterize the carbon dioxide flow that's coming out of the sample. So basically, what it does is that you first collect the aerosols onto a filter, and then you first introduce helium only, right? So then some of those volatile species will get vaporized, right? So we think about those as the organic carbon, right? So these VOC species got oxidized and then get into carbon dioxide, and we quantify them, relate them into the organic carbon. And at the same time, the remaining carbon are basically the ones that will not volatilize, right? So those are related to the elemental carbon. So under that situation, we'll introduce the oxygen into the chamber here. So to get them oxidized and further release those carbon into the air, right? And then quantify the carbon dioxide coming out of it. So in this way, basically, we can relate the carbon dioxide signal to the organic carbon and the elemental carbon. So this is basically what we can find, right? So you can find the OC, you're ramping up the temperature, right? The temperature is increasing. And then first you have the helium being introduced. Those are related to the organic carbon. So then basically when you introduce the carbon dioxide inside, then you have the elemental carbon getting out of it. Right, so this instrument is now commercialized by the Sunset Laboratory, right? So they have these OCEC analyzer system to tell you what is the organic carbon, what is the elemental carbon in the aerosol samples. Okay, so talking about these elemental carbon measurement, there are also online measurement techniques. So one example is a single particle soot photometer, or the SP2. This is SP, right? So SP2. So basically for the SP2, what it does is that it shines a very strong laser that basically the energy is very high, and for these soot particles, they're also strong absorbers, right? So they absorb this energy here, and then they can induce this incandescence. Basically, they become very bright, right? This light signal, or this incandescent signal, is basically related to how much black carbon is there in these aerosols. So there can be calibration getting established, and then basically from this SP2 instrument, just based on incandescence signal, we can calculate what is the let's say the black carbon that's in the aerosol stream there. Okay. At the same time, the SP2 can also provide you the rough sizing information because it's using the scattering signal, right? So you can, based on the scatter light signal, you can get the aerosol size distribution based on the optical sighting method. So apart from these, let's say the optical methods, we could also, since we have the offline samples, we could also use them for some other like conventional measurement situations, right? So we could use the ICP-MS, which is induced coupled plasma spectrometry, right? ICP-MS is being used for analyzing metals from the aerosol samples. You could also use the X-ray fluorescence, XRF, right? So for basically, there are a few other methods that can give you all of these metals information, and each of them will have certain limitations regarding how much metal, what is the lowest detection limit to quantify these metal, and also to, for example, certain metals, they just cannot be measured due to the instrument limitation. Okay, so if you want to quantify all of these metals, then you will need to find the corresponding instrument. For example, our group, actually, Campiemba, has been working with these ICP-MS systems to analyze the metals that's being released from the electronic cigarettes, right? So from his study, he found that we could actually see the chromium and also the, let's say, the manganese and the lead coming out of these aerosols, and they're likely coming out of the heated coil, which are being heated, right? Because you need a coil to warm up the e-liquid that's in the e-cigarette. So this high temperature here is also going to release some metal particles into the smoke, and then they can be, I would say because of that, the aerosol generation mechanism or the aerosol composition is going to be different compared to the conventional tobacco cigarettes, right? So although the aerosols, let's say from the e-cigarettes, they don't have those combustion byproducts coming out of the tobacco combustion, but because of these metal coils here, they may generate some newer pollutants that might be harmful to the human lung, right? So basically, for those aerosol chemical measurement or chemical analysis methods, they are based on the offline analysis. Well, except for the SP2, right? So nowadays there's let's say the aerosol mass spectrometer, or the AMS, is being more and more used by the aerosol researchers to look at the aerosol chemical composition in real time. Okay, so from this slide on, I'm going to use the slides that's provided by Professor Jose Luis Jimenez at the UC Boulder. So he has done a lot of work related to the aerosol mass spectrometry, and you could also check out his website. Basically, there's a very well summarized tables talking about different versions or iterations of the mass spectrometers, and he has also published many papers or attended so many projects related to the aerosol chemical characterization. We'll go over some of his work also in the course materials later on. Okay. So here, this is a very interesting figure that's summarizing the current status of all the instruments that can provide the aerosol chemical composition. So you can see that there are several instruments that we already talked about. For example, the OCEC analyzer, or the ECOC analyzer, or the PUS organic carbon, right? And you probably have also heard of the GCMS, right? So basically, if you plot the completeness, which means that how much of the mass is being analyzed, or how much of the chemical compositions are being analyzed, and also the chemical resolution for these instruments. Okay, so chemical resolution means, let's say, how much details are you getting out of the chemical composition. For example, for the OCEC, you only get the elemental part or the organic part, but you don't know exactly which are the organic part, right? It can be some carbolic acid, right? It can be related to the alcohol, right? It can be volatile organic compounds or semi-volatile organic compounds. You never know, right? You don't have the molecular information. So that's why on the x-axis, in terms of the chemical resolution, the x-axis, this is the highest resolution will provide you the molecular ID, right? It will provide you exactly what type of molecule it is, right? On the y-axis, this is the completeness of the analysis. For example, for the OCEC analyzer, it measures total mass. So 100% of these particles are being measured. But for the PUS, right? So we mentioned that it only provides you the water-soluble organic carbon. It cannot give you the water-insoluble organic carbon, right? So for some of the mass analysis, like the GCMS, they use a lone column for the particles to get attached onto the column, and then further you vaporize them and release them, basically desorb them from the surface of the tube and release them into the mass spec. Then this will heavily rely on the absorption and desorption properties of those gaseous species, right? So the GC has to be different for different types of chemical compositions. So that's why for GCMS, they're going to have a low completeness regarding particle measurement. For example, they can't measure metals. They can't measure, let's say, elemental carbon, because they simply won't get absorbed onto the tube surface, right? So then if you relate all of these, right? So definitely we don't want anything to be here, because this is just useless instrument. We cannot measure any fraction of the particle, or cannot provide you any detailed information on the instrument. But the perfect instrument will be here, which will do a complete analysis of all the particles, but at the same time provide you the molecular ID of of these chemical compositions. But you see, it's still difficult to reach there, right? So there's always trade-offs, right? Always have to balance in terms of the size range of the particles you are interested in, and also how much detailed information you want to get out of it. Okay, so here I just have a short introduction of one mass spectrometer system that's given by Dr. Jimenez. Okay, so this is a YouTube video.
What you see here is the instrumentation we use both for laboratory and field studies, but especially for some of these studies in the field where we go to the real world and measure what the pollution, what these aerosols are made of. And we can see here one of several instruments. This is an aerosol mass spectrometer. And what this does is to measure the composition. And we suck the air with a pump, rushes in. And then this part of the instrument is what does the chemical analysis. And it's all in a very compact package. It's not normally as messy as it is now. And as you see, it has wheels. So basically, we can roll the whole thing and take it to Mexico, or take it to the Arctic, or that kind of thing. And what this allows us to do is to analyze the composition of the particles of these pollutants in real time. What we do is we suck them through here. So here we have particles suspended in air. And what a particle is just lots of molecules stuck together in a piece of solid or liquid. So basically, you may have a billion molecules all stuck together. But then, even though it's a billion molecules, it's still very small. It's maybe 1 micron, which is 100 times thinner than human hair. So you cannot see it, yet it has lots of molecules. So then it's coming in. And then here, at this junction, what it does is going to impact a hot surface. So the molecule comes in, it impacts this hot surface under vacuum, because we have created the vacuum with these pumps. And then lots of molecules come flying off very quickly. So they all come flying off. And then just as they are flying off, we have a filament, a hot filament like in a light bulb, and we are raining electrons on them as they try to basically escape away because they've been heated. That interaction produces some ions, and that's what allows us to do the analysis. Once we have ions, we can basically steer them with these electric fields. And so what we do is we steer them into here, and then we make them fly like this in this box. This is called the mass spectrometer, so they fly like this. And then we finally detect them. And what happens in this thing is we basically give all the ions the same push, but what you find is that the lighter ions with the same push end up running faster. The heavier ions, you give them the same push, and they go more slowly. So after this distance, some of them arrive earlier, some of them arrive later. That's what we call a time of flight mass spectrometer. We just measure the time, and then we can relate the time to their chemical composition. And that's how we know what the particles are made of. And this is a technique that's used in many instruments in laboratories. What's more unusual here is that we're actually packaged it in a system that you can see has wheels and is in a rack that we can use to start rolling this over and take it, if I remove the brakes, and then we could take it to Mexico, we take it somewhere else and do that analysis there. The instrument allows us to do a couple of things. One, it allows us to determine how much of these different pollutants is there, and also what the pollutants are. So you may be flying, for example, through a volcanic plume. You may see that there is a lot of sulfur, because volcanoes make sulfur, and that's what then they make particles of. If you fly through a forest fire, you may find a lot of organic material, because trees are made out of cellulose and organic material, and then when you burn them, you basically put a lot of that carbon-based material, that organic material, in the air. And why these instruments are so interesting, and why people want us to participate in these experiments, is because we can do both. We can tell what they're made of and how much is there. That's really the combination that's powerful.
Stop.
Okay, I think this is a very nice summary of the mass spectrometers, right? So then here we'll just introduce different types of mass spectrometers. And actually, we'll first give an overview. What are the advantages of the mass spectrometers? Okay, so why do we use aerosol mass spectrometry? It has several advantages, right? So mass spectrometers are extremely sensitivity. So if you recall for the DMA, right? So when we're selecting particles, we're just using like an electric field to select particles based on their mobility size. But then if you think about, let's say, compare a particle of 11, let's say 10 nanometer and 11 nanometers, right? So although they're just off by 1 nanometer, but their volume can be off by a lot, right? By almost 30%, right? If their volume is off by 30%, then their mass is off by 30%. And this 30% extra mass can contain different types of chemical compositions in there, right? So if they have these different chemical compositions, then you won't be able to detect them based on the DMA, right? So this is where we're going to use mass spectrometer, which are more sensitive to these mass and then which are further related to the volume of the particles. They also have very fast responses because it's related or is depending on the travel of the particles within the detection region of the instrument. So it can be very short in terms of their travel. It has a universal detection of all the different chemical compositions. You can ionize them as long as they can get ionized, then you can detect no matter which type of molecules they are. And you can also field deploy them because they are, you just need a few turbopumps and electricity and maybe some calibration standards to use these instruments. Okay, but the challenge for using these aerosol mass spectrometer is that how do we interface the aerosols to the mass spectrometer? Because mass spectrometer is not limited to the aerosol field. Actually, it was heavily used by the medical field, right? So whenever you're trying to do the blood test, try to determine what's the glucose level or different chemical composition in your blood, people use mass spectrometer to detect them, right? It's being used in the medical field, the chemistry field, physics field. An aerosol field, I would say, is a small field that's using these mass spectrometers. So the difficulty for the aerosol mass spectrometry is how do we introduce these aerosols into the mass spectrometer, right? We first, because normally the aerosols are relatively large and the mass spectrometers normally will have a mass range of up to, let's say, 500 mass over Z or the AMU or elemental mass, right? So if it's 5,000, then if you consider the volume of a spherical particle, maybe the diameter is still within a few nanometers, right? If that's the case, then we can't really detect the very large particles that's suspending in the air. So we have to break them apart. We have to fragment them and at the same time introduce a charge to them, right? So that's why people call this process also like a miracle process. And I think there's a recent publication saying that they call their ionization and also fragmentation method called the magic method, right? Basically, you're fragmenting it without a certain rule, right? Or we have a general set of rules, but since these chemical compositions are unknown, so we really can't use we can get a rough understanding of what these particles are made of, but we can't get the exact quantification of their chemical composition. But basically, after this fragmentation and ionization process, you will get different types of ions. For example, the ammonium ion, the, let's say, sulfur oxide ion, or some hydrocarbon ions. And then after they're charged, then we use the, let's say, the movement of these ions under the electric and the magnetic field to separate them based on time that they travel in this system here. Okay, so first we'll talk about, let's say, the earlier part, let's say the general mechanisms or general principles of the mass spectrometer. And then we'll give a few examples of the mass spectrometers being used in the aerosol field. So basically, in terms of the structure or the detailed, let's say, the components of an aerosol mass spectrometer, it will include the aerosol interface and the mass spectrometry part. Okay, so the mass spectrometry part will include ionization and mass analysis. Okay, so this is quite universal because all of the mass spectrometers need to have their, let's say, the analytes being charged and then being analyzed in the mass spectrometer. And then there's also this aerosol interface. And currently there are so many different types of interface that people can use. And different interface will also select particles of certain chemical composition. It really depends on what type of aerosols you're trying to look into. Okay, so basically, as Professor Jimenez pointed out, basically each pass here or each instrument correspond to a specific pass, right? So if you consider all of these combinations, it can be around 1,000 types of combinations, right? And currently there are around 30 types being used. Okay, and each type of mass spectrometer are advantageous for detecting certain type of aerosols or providing certain feature of the aerosol measurement. Okay, so first we'll talk about the aerosol inlet. Okay, so what type of inlet we're trying to use. So basically for these aerosol mass spectrometers, we introduce them into, or most of the time, we introduce particles as a beam. Okay, so if you consider the environment in the mass spectrometer, so inside mass spectrometers, those are the vacuum conditions, right? So basically the pressure will be reduced to 10 to -5 torr, which is close to, let's say, around 1 Pascal, right? So you need to reduce the aerosol sample from the ambient condition, which is close to 1 atmosphere, all the way down to 1 Pascal, right? So during this process, you have to reduce the pressure, and at the same time, you want to maintain a similar level of aerosol concentration in there. Because if you just divide it based on the proportion, let's say you reduce it by 10 to the fifth, right? If you also reduce the aerosol number by 10 to the fifth, then you won't be able to detect much of the particles, right, or their mass. So because of that, in the aerosol inlet, we also need to concentrate these aerosols from the gas phase. Okay, so basically, if you consider how much we have to concentrate, it is or the particle concentration in the ambient environment. It normally, let's say, the ambient environment is close to 10 microgram per meter cubed, and if you compare that against the gas density, right? So the particle, let's say, the mixing ratio is 10 to the -8, right? So we have to concentrate them. And if you just do everything based on the ratio, then if you reduce that to 1 Pascal, then this particle concentration will get reduced to 10 to -13, which is not the ideal situation for us to detect their mass concentration, because the concentration will be too low, right? And also you want to reduce the gas phase interferences, because you don't want any reaction to happen at the surface of the particles, right? So normally people will also add a denuder to get rid of the extra gas species that are in the aerosol sample. And also, since there is this pressure reduction process, and actually, if you reduce the pressure, then there's an acceleration of the particle velocity, right? Because you're trying to pull the aerosols through a tiny hole. So then if there's an acceleration, then different particles with different sizes, they're going to have different aerodynamic property, right? So larger particles, because of the larger inertia, they will move slower. Smaller particles will move faster. So you can separate them based on the time of flight properties of these aerosols. Okay, so particle beam mass spectrometer is, I would say, is the most common system that people use for the inside the aerosol mass spectrometers. Okay, so we can take a look at the let's say the particle beam, or or basically the aerosol interface that's being installed for these aerosol mass spectrometers. So what happens is that in the ambient environment, the aerosols can be existing in different locations, right? And then we have different stages, basically try to minimize the nozzle little by little, right? And then reduce the pressure until, let's say, it's close to the pressure that's in the mass spectrometer region. Okay, so you can see basically if we have particles, and then if we can also follow the flow well, right? And then they can get concentrated here. And then since we're pulling out air to reduce the pressure, so for each stage here, we're pulling out air from the side, right? And then you're trying to reduce the pressure gradually. So then the particles will get pulled out, and then since they follow the flow, especially with smaller particles, they will get concentrated again and then move to the outside and then concentrate again all the way down. That's so they're concentrated eventually through this nozzle. Or we also call this as the aerodynamic lenses. Basically, you're concentrating this beam. It's almost like a magnifier, right? You're concentrating solar light to a single dot. It's the same process here. You're concentrating all of the particles into a single or a very narrow beam here. So as you can imagine, we're talking about particles that can follow the flow. So what about particles that cannot, right? So if you have very large particles, for example, supermicron particles, let's say 10 micron, 20 micron, then after they pass through here, even if they move out, they won't be able to pass by the nozzle, right? So they'll get lost at this lens here. Now for the small particles, since they move similar to the gas, they may also get diffused to the outside and get removed, right? So there's always a window that the mass spectrometer can, a window of particle size that the aerosol mass spectrometer can detect. We'll talk about that window later on. So there have been studies trying to simulate or to understand how the particle move in the aerodynamic lenses, right? So you can see if you're introducing 5 nanometer particles inside, which are very small and diffusive, then they will move closer to the outer wall. If you're introducing larger particles, right? So then they will follow the streamline pretty well. If you're introducing even larger particles, this is 10 micrometer, then I would say most of them, or the ones that facing this stage here, will just get collected and then get removed by the aerodynamic lens here, right? So because of that, you can imagine there's going to be an efficiency. So for the small particles, they have a smaller detection efficiency, and for the very large particles, they have a lower detection efficiency. Only the middle, you have a high enough efficiency to be detected. Okay, so this is an example of how the particle beam actually looks like. So it can be very narrow. And there's also a study showing that you can basically build a tower out of this beam here. So you just deposit aerosols little by little and then get a very narrow structure out of the particle beam or the aerodynamic lens. Okay, so this is again showing the different pumping of the gas species, right? So for the aerosol mass spectrometers, you have different turbo pumps, right? Or the rough pumps, or different types of pumps to pull the flow out of different stages. So in this process, you reduce the pressure all the way down to the inlet of the mass spectrometer. At the same time, you can control or you can focus these aerosols into the beams. Okay, so overall, for example, in the aerosol mass spectrometer, the particles will concentrate by 10 to the 7th with respect to gas. Okay, and since you are basically extracting these aerosols through this narrow diameter or narrow nozzle here, as you can imagine, smaller particles, right? So they will move directly with the flow. The larger particles, they have larger inertia, right? So they're less likely to follow the flow, right? So because of that, the larger particles will also move slower, right, compared to the flow. So you can, based on how fast the particles eventually reach to the mass spectrometer region, and then based on time, you can relate it back to the aerosol size. This is very similar to the APS, the aerodynamic particle sizer that we introduced at the beginning, right? So, well, upon the expansion into the vacuum, particles acquire a size-dependent velocity, and it's already there, right? So you have different stages of expansion and then focusing, right? You may as well use it to measure the particle size, right? Smaller particles move faster, larger particles move slower. And then to measure the particle size or particle time of flight, you can use a similar method compared to the APS. You just have two I would say two laser beams, and then the particles can pass through the beam, and based on the time it travels, you can relate that to the aerosol size. Okay. So actually for the mass spectrometer, aerosol mass spectrometer, since you have different levels and the pressure is reduced all the way to close to 1 atmosphere, right? So then the aerodynamic sizing can be very accurate. So people have been calibrated these sizes For example, this is showing the aerodynamic diameter in terms of the nanometer. You can see each of these peak is very narrow, right? You can have a resolution of 30. Remember, for the SMPS system, normally we use a resolution of 10, right? But for the mass spectrometer, since there's a very long process for the particles to reach to the, let's say, the low pressure to the vacuum, or the pressure close to the vacuum, then it can give you a very accurate sizing of the particles. So then you may imagine, well, you're introducing aerosols continuously. How do you get the particle size distributions? Okay, because you're always going to have smaller particles reaching to the detection, like let's say to the laser, and larger particles reaching to the laser. But how do you differentiate? Right, so you could measure their size distribution just by using a chopper. So basically, a chopper, on a chopper you have a very thin slit here, right? So when it's turning, most of the time it's just blocking out the particles. When it's at the right angle, you're introducing a stream of aerosols inside. And then inside the stream, smaller particles will reach the laser faster, larger particles reach to let's say larger particles reach to the laser slower. So in this way, you can directly get their aerodynamic size distributions. And after you get the size distribution, let's say measured every 1 minute, and then the rest of the time can just be introducing all the aerosols into the mass spectrometer, so you get the total chemical composition. Let's say you have enough of the particle mass, and then you can get very good signal, let's say in terms of their mass spectrum, right? So as I introduced earlier, for these aerodynamic lenses, they will only work for a specific window of particle size, right? So for the very small size, they can't get detected because they're too diffusive. They'll just go with the gas. For the very large particles, they also won't get collected because they have the large inertia, right? So, I mean, a fraction of them will collide onto the stage. So only the one that goes through the center can get collected. So that because of that, you will have a specific window where you introduce the aerosols into the mass spectrometer. Okay, so because of that, here's a summary, right? So no inlet can transmit all of the sizes, and the most common aerodynamic lens will introduce or being used, and most common aerodynamic lenses are the submicron lenses. And then there are also some other types of like custom lenses to focus on specific size range of the particles. Okay, so we talked about the aerosol inlet and how they size the aerosols. Now we can talk about the mass spectrometer region, right? So I'm not sure if any of you used the mass spectrometer before, but currently there are two major types of mass spectrometers. I would say multiple types of mass spectrometers, and there are two types that's widely used. One is called the quadruple mass spectrometer, and the other is called the time of flight mass spectrometer. Okay, so the quadruple mass spectrometer, as the name means, right? So you have four rods here. So each of the rod will contain certain high voltage or certain voltage, and also it has certain frequency for, let's say, changing the voltage, right? So the ions are being introduced into, let's say, the gap or the center of these four rods here. And then since the voltage are changing, right? And then it's using AC and DC voltages. So the ions are going to move around, right? And then basically for certain ions, because of this electrostatic force, they will get spin out. They won't be able to go along the center of these center line of these quadruples, right? And then there will be some ions that with certain sizes, with certain mass to charge ratio that can penetrate through the quadruple and then further get detected by the detector. So we call these, let's say, classified ions as the resonant ions, and then the ions that are not being classified as the non-resonant ions. Okay, and for the resolution of these mass spectrometers, right? So basically, the ions that are being detected, only the ions with certain mass to charge ratio, or the mass over Z, can get detected or get classified and then get detected by the mass spectrometer. And you can further relate their intensity to the concentration, right? And also the voltage setting to their mass to charge ratio. And then this is how you can get their mass spectrum. So in terms of this classification method, or this selection method, so the quadruple mass spectrometer will have a resolution of around 0.1 AMU, or 0.1, let's say, the mass to charge ratio. Okay, so if you think about, let's say, if we're trying to measure the water ions, right? So hydronium water ions, which has a mass of 19, right? So then if you consider the mass to charge ratio, or this resolution, you'll get something close to, let's say, 18.9 to 19.1, which is okay, right? So if you know that this is hydronium water, right? So the charged water molecule, then you would expect something to be like that. But the thing is that a lot of times we don't know what the source is, right? If you see a mass to charge ratio of 19, then it could also be, let's say, some hydrocarbons, right? It can also be, for example, some other species that has the similar mass to charge ratio. And we're just talking about 18 or 19. When you get to the range of hundreds or thousands, then there can be so many different combinations that it's difficult to get really what is from this chemical composition or from this species. Of course, there are ways that we can, based on the general pattern of these mass, let's say the mass spectrums, and then try to relate to certain sources. For example, in general, the combustion sources, let's say biomass burning, they will have certain a pattern of the mass spectrum, or from the, let's say, the clean forests, they will have another type of spectrum, or from the industrial process, there is another type of spectrum. So you can relate these in general to certain sources, but you cannot tell exactly what are the chemical compositions. So because of this lower resolution, and it's also relatively simple to build, right? So for the quadruple mass spectrometers, their cost is also lower, their size is also smaller. So I would say quadruple mass spectrometer is still the most widely used mass spectrometer in all the different types of labs. Okay, so so I would say in the medical field, maybe people use these more because we know what we expect from our blood, right? So if you want to measure the glucose level, then you would expect something to show up at a mass to charge ratio of certain value. So you can just relate that value to the glucose, right? But if you're talking about atmospheric aerosol compositions, there are different types of compositions. It's basically combinations of hydrocarbons, different types of hydrocarbons. Then it's going to be challenging to identify which type of molecule they are specifically are, right? So the other type of mass spectrometer is called the time of flight mass spectrometer. So the time of flight mass spectrometer, basically it uses time of flight method to separate the ions of different chemical or different mass to charge ratios. So you can ignore these regions here. Okay, so this is basically what people call a triple quadruple. Okay, so you have different quadruples here, but most of the time we don't need this for the time of flight. So time of flight is mainly for this region, where we introduce the ions of different mass to charge ratio, and then there's this accelerator. Accelerator is using basically different electrostatic field to accelerate these ions, right? So on the other side, there can be what we call the ion mirrors that use certain, let's say, the electric field or magnetic field to divert these ions, okay? And basically, if you consider the energy balance for the particles or for the ions traveling in the mass spectrometer, so their kinetic energy is related to the electrostatic potential, right? So no matter what their mass is, they all have the same electrostatic potential when they pass through these different devices. So basically, they're being converted into the kinetic energy, and the kinetic energy is just 1/2 multiplied by the mass of the ion multiplied by the velocity squared, right? So the larger the particle or the larger the ion, the smaller the velocity. So that's why if you have a smaller velocity, then you will have a longer time. You need a longer time for the ion to reach to the detector eventually. And also, since for these time of flight mass spectrometers, they can design their device that they can have what people call the W-shaped time of flight, W-shaped trajectory, right? If it's a W-shaped, then you have a relatively longer trajectory before they reach the detector. They can also have the U-shape or the V-shaped trajectory, which they just go through the region once, right? And then go to the eye mirror and get reflected to the detector. So you can have different trajectories or the different total distance that travels, right? And then because of that, you can get particles or ions of different times or time of flight before they reach the detector. So normally these time are relatively long, right? Or these, I would say these trajectories are relatively long. And because of this long trajectory, you can get a higher resolution in the mass measurement. So for example, many of the time of flight mass spectrometer can have a full width half maximum of 0.0001 AMU, right? So if you consider that, this is very high accuracy mass measurement, right? And then because of these, the complexity of the time of flight mass spectrometer, the cost is higher. There's also their size is also becoming larger. Right? So then you may wonder, well, why do we need this high accuracy of the mass, right? So then if you look at the periodic table of the elements and look at their exact mass or atomic mass, right? So you see a lot of them have mass that are not integers, right? For example, oxygen have 15.999. So if you have a mass spectrometer that can give you a high accuracy in their molecular mass, then you can even make the combination, right, to directly add them up together and then match it with the mass that you measure for this molecule here. For example, let's say if you have water, again, hydronium ion, let's say the water attached with the hydrogen ion, right? So then you will have H2O, that's going to be two hydrogen with one oxygen, and then one extra hydrogen. So you will have let's say a value of 19 point, let's say 0.023, right? 023, 19.023 at the end. But if you have the high resolution time of flight mass spectrometer, right, it can give you the exact AMU value here, or the exact mass value here. So you can directly know, well, hey, this is the water molecule attached with a hydrogen ion, okay? So because of that, you can directly identify what type of chemical composition it is for these ions here, right? So that's the advantage of the time of flight. Okay, so now we can give a few examples of the mass spectrometers that people normally use in their studies. So here, I think Dr. Jimenez further classified the vaporization and ionization section based on different types. So we talk about the aerosol inlet, these dynamic lenses, the particle sizing, like time of flight. We talk about the mass analysis, right? So then the question is, how do we convert the particles into the ions, right? Because the particle size can be large, let's say 100 nanometer. If you calculate its mass, it's probably going to be millions of AMU, which is over the range of the common mass spectrometers, right? If it's over the range, then you have to fragment it, you split it into different molecules or different ion species. So you have to vaporize it to get the smaller molecules, and also you need to give these molecules charges so that they can get analyzed in the mass spectrometer. So basically, it's being for these vaporization ionization devices, they can get separated into two types. So type 1 is the laser evaporation. You shoot a laser to vaporize them. There can be, let's say, the common laser or IR laser or UV photoionization. You can also use thermal vaporization. So instead of using the lasers, you can just heat it up, right? So the impact hot surface, heating the gas, or send electrons or electron attachment, chemical ionization, and so on. So further, there can be different types of ionization method. There can be hard ionization, which is fragmenting all of the species into tiny molecules, or there can be soft ionization methods, basically to attach, let's say, a single electron or attach a single hydrogen onto the molecule and then to detect them, right? Instead of breaking them apart and fragmenting to all of the tiny pieces. So, for example, there can be type 1A. Type 1A will mean that laser evaporation, and then it's using the hard ionization. So examples can be the particle analysis by mass spectrometry, the PALMS, and the aerosol time-of-flight mass spectrometer, the ATOF MS, that's made by Dr. Kim Prather at UCSD, right? UC San Diego. And then single particle laser ablation mass spectrometer, or SPLAT, that's made by Dr. Ala Zelenovic at PNL, right? So basically these mass spectrometers, they share the same category, but they use different detailed mechanisms for laser vaporization or ionization. So this is a PALMS instrument. For example, this is also pointing out which combination they're using, right? So you introduce the aerosols, and then you ionize it, right? And then they're being introduced into the time-of-flight region. So the same thing for the ATOF MS, right? So here, actually for the ATOF MS, it has two time-of-flight region, right? One is for measuring the positive ions, one is for measuring the negative ions. So for the PALMS, it's actually being, has been, or it was deployed onto the wings of a research aircraft, right? So to monitor the chemical composition of the aerosols. So it also did measurements in the stratosphere, right? It's very high up in the atmosphere. I would say the mass spectrometer will feel much better under low pressure, right? Because at that time you need less amount of energy to bring the pressure all the way down to the ambient pressure. And basically from the analysis, you can see that there are quite many interesting findings. You see a lot of ions, right? You see iodine and also mercury. And mercury is probably related to the human activity. So you clearly see that there are some human processes that's influencing the air that's in the really high up in our atmosphere. So then there are basically differentiations in terms of the ensemble measurement that measures everything in the particles, like all the particles being introduced or being vaporized, being ionized, or you analyze them based on like a particle by particle analysis or the single particle analysis. So you remember for the let's see. Yeah, remember for the mass spectrometer, for example, the ATOF MS, right? This is using a single particle. Actually, for the SPLAT, it's using a single particle measurement, right? So if you measure the particle mass composition in a single particle condition, right? So then you will get a more understanding, like a full picture of what is the mixing condition of the particles, right? Because you can have a mixture of, let's say, sodium chloride particles and ammonium sulfate particles. So they can be separated from each other, but also they can be like merged together, right? Or what we call the externally mixed or internally mixed, right? So in this case, using single particle mass spectrometer can tell us which type it is. Are they internally mixed or are they externally mixed, right? So there can also be type 1B systems. So B here means whether they're using the hard ionization or the soft ionization, right? So basically, if you use the soft ionization, you have a higher signal, let's say, and at the same time, you see lower fragmentation of the molecules. So there can also be type 2A systems, which are using these heated conditions. Instead of using laser, you can use a heat surface and also use some, let's say, the heat the gas up, right, to introduce the to basically vaporize these molecules. Okay, so examples can be the aerosol mass spectrometer. This is a widely used instrument that's manufactured or commercialized by Aerodyne. There can also be thermal desorption particle beam mass spectrometer or thermal desorption aerosol GCMS or the TAG system. So for these systems, they basically collect the particles onto a surface and then they heat up the surface, right? They'll use a hot surface. And then for the AMS, they're using the electron impact method to charge the particles and then further measure the chemical compositions. So from the AMS, it can directly tell you, let's say, what type of, because it has a high resolution measurement, it can tell you what are the major species in the particles. It can be ammonium, nitrate, sulfate, organics, or chloride, right? So it can tell you what are the fractions of these different chemical compositions. And here are some more references talking about how these analyses were done, right? And then there can be comparison between the AMS with other measurement techniques. For example, here is comparing the TEOM, right? So the AMS with the TEOM measurement in terms of total concentration, and also comparing that against the let's say the water-soluble primary organic matter. So you can see water-soluble is not the entire fraction. It's not the entire, let's say, the ensemble of the organics being detected by the AMS. There is also non-soluble species, right? But the ammonium, sulfate, and nitrate, they correspond pretty well with the different types of measurement. So it's comparing against the PEWS, right? PEWS is particle into liquid sampler that we introduced earlier. It's used in offline analysis. So you can also compare that against the SMPS in terms of the total mass concentration, because AMS also give you the size distribution of the particles, right? They're based on the aerodynamic size distributions. Okay, so I think we can pause right here in this class, and the next class we will try to finish the mass spectrometers and then talk about the aerosol calibration standards. Okay.